Welcome back. We were talking about one of the important parameter of the stations, Earth station, is G by T, that defines the receive characteristics. And since there is a different types of antenna, small to large, which are available, G by T is the antenna gain G, and T is the noise temperature. Measuring this G by T becomes difficult because you have to put two noise sources at the input of the antenna of the receiver. So, how do we do it in case of, particularly in case of very large station? So, for a very large antenna which is of the order of 9 meter or even bigger than that, direct method of G by T measurements are there, and technique is similar to Y factor measurement. So, two calibrated noise source required. How can we get it? Now, sky is one of the very important area towards which this receive antenna is looking. Now, we can use the sources in the sky itself. So, we can use some radio stars. That means some stars or a combination of stars in that particular direction emits radio noise in various frequencies. In our frequency of interest, which may be 4 gigahertz or 12 gigahertz or things like that, it emits, we receive on the earth some power flux, and people have done a lot of measurement on that, our radio astronomy people, and those are very helpful to us. So, it has been found that in some direction, in some of the constellations, these radio stars are there, and these some radio stars, their flux density or power flux density reaches earth are well measured, and they vary slowly with time, and this time is of the order of years. So, during the measurement it does not vary, therefore, during the measurement we can assume it is a constant source, and where the radio stars are not there, other direction of the sky, if of course the sun and moon excluded, other direction of the sky, there is general galactic noise which is coming, which is almost constant. So, we can call it cold sky. So, we find two reference noise sources in the sky is the radio stars, whose directions and locations are well known based on the time, and other than that is cold sky. We exclude of course sun and moon. So, some of them I show you some numbers. One is Cassiopeia A, it is a radio star. It emits and earth receives 1065 into 10 to the power minus 26 watt per meter square per hertz, and this was at 4 gigahertz, measured in January 1968, and the diameter of this radio star is 4 minutes dia. There is another one which is Taurus A, whose emission is 717 into 10 to the power minus 26, the same unit watt per meter square per hertz. Then similarly, another is Cygnus A, 488 into 10 to the power minus 26 watt per meter square per hertz. So, like that many are there, we can point to any one of them. So, let us see how the measurement is done. So, point antenna to cold sky, that means the direction on which this radio star is not there. So, measure through the receive antenna, through the receiver including the antenna, the noise power is P1, let us call it K Ts P. This system noise temperature, which includes the cold sky noise temperature through the antenna. Now, then point antenna to radio star, any one of them, then receive noise power P2 is now 0.5 the flux density, the aperture of the antenna and the bandwidth plus its own KTB noise. So, this is P2, where F is the flux density, AE is the receiver antenna aperture, effective aperture, and 0.5 is because of the polarization is random, the noise which is coming, its polarization is random. So, 50% is taken. So, Y factor is P2 by P1 is half F A E B plus K T S P by K T S P. This P2 is this value and P1 is K T S P. Now, if we interchange this, or first we can do it this way, that is, this K T S B is 1 plus half of F A E B by K T S B. So, we can call it this way, what y minus 1 is half of F A E B K T S B, and then B gets cancelled. So, therefore, and in case of A, if I put the now gain of the antenna, so it becomes half F G lambda square by 4 pi, then 1 by K T S. We can rearrange and we can say it is F lambda square by 8 pi K into G by T S. This G is G R, so it is G by T. So, in terms of this, it is coming out. Now, that means the you can interchange that, is we can write fresh, that is G by T is equal to y minus 1 into 8 pi K by F lambda square. So, once we know the power measured, once we know the clear cold sky power measured through the receiver including receiver antenna, and point towards the radio star and measure another power, take the ratio of y, we can calculate that ratio y as y is calculated. K is a Boltzmann's constant. For that particular radio star, f is known, lambda is the frequency what we use, and accordingly we get the G by T. Now, this G by T needs certain correction, because if you remember that f we said at 4 gigahertz it was measured, and you may not be measuring this your station may not be working exactly at 4 gigahertz, it may be slightly away from 4 gigahertz. So, there has to be correction factor based on that. There has to be correction based on the elevation, because when you are looking at the at the radio star which is at much lower elevation angle, that other type of noise may come. So, there has to be some correction. There has to be some correction based on year to year variation of this flux density f, which is coming from the radio star. So, there are a lot of corrections which are to be applied, which could be in dB, and accordingly the G by T, which is the corrected value, is based on G by T, which is measured plus some correction factors. So, this is one method of doing the direct measurement of the G by T using the radio star. Now, there may be some smaller antenna and which can have a larger beam width. Now, when you see with a larger beam width, the radio star flux density is at one single point and other noises may come in. So, it is better to use a different method, which is called indirect method. So, for a medium and a smaller antenna, we use indirect method of calculation. So, this is indirect method. For medium and smaller antenna. So, here we do it this way. We have the we measure GR separately. In anechoic chamber, or test range. And then measure T separately. So, for separate measurement of T, we let us put the receiver whose noise temperature has to be measured, and we put 3 input sources. One is the antenna, that particular receiver's antenna. One is a noise source at a higher temperature, and another is a dummy load at normal temperature. So, 3 measurements are taken on a power meter. Let us say when it is connected to the antenna, we measure power as P A, which is K into the temperature of the antenna and temperature of the receiver, and KTB. So, when it is connected to noise source, then P n is equal to K, temperature of the noise source, temperature of the receiver, and B. And when it is connected to load, that is at T 0, that is normal temperature, we call it P 0 is K T 0 plus T R into B. Now, we take the ratios of this, and that we get y factor 1, y 1 is P n by P A, which is that K and B gets cancelled. So, we have T n plus T R by T A plus T R, and y 2 we call it P, that dummy load, by power measured through antenna, and then it is T 0 plus T R by T A plus T R, and you take y 2 minus y 1, which is P n minus P 0 by P A, which is Tn plus Tr minus T0 plus Tr by Ta plus Tr, which is equal to Tn minus T0 by Ta plus Tr. Then we can write Ta plus Tr is equal to Tn minus T0 by Y2 minus Y1. The Ta plus Tr is antenna noise temperature and receiver noise temperature. So, this is nothing but the system noise temperature. So, the system noise temperature is now Tn minus T0, this is normal temperature, and this noise source for which temperature is known, which is higher. These two are known, Y2 and Y2 and Y1 are already measured power ratios. So, you can find out in this method the Ts. G is already measured. So, G by T is calculated indirectly now. There is another indirect method using satellite itself. You know, the satellite transmits beacon signal. That is to track the satellite. Where is the satellite? Is for large antenna to point to the satellite. There is a constant EIRP, a particular frequency, without any modulation it gets transmitted. It is called beacon transmission. So, beacon signal transmission, for that beacon EIRP is very well known and well calibrated. It does not change, otherwise the pointing error will be there. So, you can use this beacon signal reception as a G by T measurement. So, it is simply we have to assume something, that is the beacon EIRP does not change during measurement, and of course, it is known, the value of that is known. Then the losses in downlink are known. Then the straight equation G by T is C by N naught down minus EIRP of beacon plus losses plus K. So, if you measure the C by N naught of the downlink, this is the measured, and EIRP of the beacon is known, losses are known, K is a constant. So, therefore, G by T can be found out. So, this is a indirect method using the satellite. Assumption is losses are known and EIRP of the beacon does not vary during the measurement. Now, there is one more method which is called comparison method. This is very simple, that is this is used for many stations which are small and medium station. A reference station is used whose G by T is known. Now, co-locate the station under test with reference station. Since they are co-located, the path losses are same, and you measure the C by N naught of the beacon. So, the reference station measured C by N naught will be C by N naught reference in the downlink, of course, is equal to EIRP of the beacon plus G by T of the reference station minus the losses minus k, and the C by N naught of the test system is EIRP of beacon plus G by T of the test system minus L minus k. This is unknown. So, C by N naught of the reference station minus C by N naught of the test system is equal to G by T of reference station minus G by T of the test system. These two are measured, this delta C by N is measured. So, G by T of the test system is equal to G by T of reference minus the delta C by N naught of these two measured value. So, this is simply by comparison, by co-locating a station you can measure the G by T of a test system. Now, the G by T, the many methods we have talked, that is direct method, indirect method, and indirect method, two of them from the satellite, and using some power meter measurement, and also by comparison method. The other important parameter is EIRP. So, in this case, of course, we have to have certain separate measurement, that is measure transmit antenna gain in anechoic chamber or test range, antenna test range, and then measure power, transmit power output separately. Multiply these two, you will get the EIRP. Now, this is the power amplifier or high power amplifier. So, this is our PT. Now, that is passed through a directional coupler or branch line coupler, high power coupler. So, couplers does what? It keeps a throughput through which directly the power goes, and it couples some sampling power out of it, that is at certain ratio. Say if it is a 10 dB coupler, so you will get PT minus 10 dB. If it is 20 dB coupler, PT minus 20 dB. So, 1/100th of that is taken out, and that you put on a power meter. So, as you go on increasing the power, PT changes. So, therefore, a coupled power is measured, rest of the power goes out, but simply rest of the power does not go out, there is some loss in this. So, the power which goes out is PT minus the coupler loss, minus the coupler loss. So, this is our transmission which is going to the antenna, and this in between there may be the waveguide loss, which so there will be a total feeder loss. So, this part is part of feeder loss. So, now the PT is known and feeder loss is known. So, this multiplied by GT, which is measured, gives us the EIRP. So, that is how we can calculate the partly measure and partly calculate the EIRP of the system. So, with all these things, we have in last couple of classes we have covered the ground segment, And what was covered is the types of earth station and their antennas, then the need of hub station for VSAT, or it is true for smaller terminals. By that I mean that the mobiles or sat phones also will need hub station. The need for that, we did some calculation, and then we have subsystem blocks of a station, and then also we have measurement techniques for a station parameters like G by T or EIRP, etc. So, the ground segment, more or less we have now a good idea. We did not go into the detail of the devices used in the ground station. These are common for any type of transmit receive wireless communication system. But in general, for satellite communication, what type of ground station, how it is measured, what is the antenna characteristics, all these things we have seen, and how the antennas are mounted, etc. So, thank you very much. We have covered up to ground segment. We will continue with other topics in next class.